justify that, we have to look back some historical events. The historical event is as follows. The first historical event we have to trace back to 1957. In 1957, I was a sophomore in college. I was the second year at National Taiwan University. And that year, a historic event occurred. That's the Sputnik satellite. In October 4th, 1957, Sputnik was launched. And this event shocked the whole world, especially the United States. Yeah. And in fact, the United States, after they seen Sputnik, they immediately reorganized a lot of things, including education system. And I will tell you that I was influenced by this shock. And after that shock, at that time, the president of the United States was President Eisenhower. So Eisenhower, in October 1st, 1958, a year later, reorganized NACA. NACA is a committee to study aeronautics. But then they find that's not enough, because aeronautics does not go into space, does not go into orbit. So President Eisenhower, in October 1st, reorganized NACA into National Aeronautic and Space Administration, and short for NASA. So 1958, that's the first time, in response to Sputnik. Without Sputnik, NASA would not be there. Okay. With Sputnik, Eisenhower reorganized it. And after reorganized, most of the energy NASA spent is try to build a bigger rockets, send something into space. But that United States is already way behind Russia. Russia has already such powerful rockets that can send a satellite into space, and the United States still playing with the little rockets. So after NASA get organized, NASA's main job is to try to catch up with the launch capability. So how we build a bigger and bigger rockets. And there's lots of frustration. United States want to impress the world that we have the capability to launch a satellite. Every attempt failed, and failed miserably. Okay, you try to launch a satellite to explode on the pad, and sometimes go just before get into orbit to explode. So after all this frustration, by the time to Kennedy, and Kennedy is a young president and is very daring, he has a vision. So he immediately got his staff to say, listen, we cannot suffer this failure, especially when Kennedy first becomes president. There are lots of other things happen. First, he tried to invade Cuba, and that ended up in miserable failure. The invasion force was wiped out, and lots of people get captured, and they say, well, we are supported by CIA and all that. So United States lost a lot of faith. So in the world, United States is a failure. You cannot manage your backyard. You cannot get this satellite into space. So what kind of good thing you can do? So under that condition, in 1961, President Kennedy, of course, he did some homework. Okay, President Kennedy, the homework he did was he called the NASA administrator in. Says, I want to do something really dramatic. I know you cannot do it in a year or two. Let's set a faraway goal. And this faraway goal is to land somebody on the moon and bring the person back. And that's unthinkable, you know. At that time, United States barely can launch a little satellite into space, into an orbit. And then suddenly you say that I'm going to launch a person into not only space, get to the moon and come back. Okay? And this is a big challenge. And but Kennedy made a calculated take a calculated risk. He figured that the United States has a very deep research capability that reside in all the research universities and in the national laboratory. And the United States has strong enough industry to support whatever the scientists will come up with. So he thinks that if we set a near goal, then the inertia is so big they cannot move fast enough. So they decided to set a far away goal. And so he brought the NASA administrator in his office, and he said that I want to go to the moon. The NASA's administrator's jaw dropped. He says, what do you talk about, go to the moon? We cannot even launch a big enough satellite into space. How can we go to the moon? He said, well, if you cannot go, step aside, I'll find somebody can do it. So then the NASA administrator said, fine, we're going to do it. So after they did some preliminary calculation, they think that maybe in 10 years they can do it. So then, with that information, in May 25th, 1961, Kennedy went to the Congress. In joint session of the Congress, he said that we're going to challenge whoever, but by whoever he actually means Russia. Okay, we're going to challenge you for a big race to the moon within the 1960s, within 1 decade. Within 10 years. And everybody listened to that, thought they were kidding, because United States cannot even match the satellite launching capability with the Russia. How can you think of going to the moon and come back? So the United States put all the money in that. And Kennedy told NASA, money is not a concern. This is a blank check. You do whatever you want, okay? If it costs money, we'll give you money. If you need more people, hire more people. So NASA, once it's formed, hired 100,000 engineers and scientists. How many NASA employees, when I left NASA or around this time, less than 40,000. Okay, from 100,000 dropped to 40,000. So the peak of NASA is 100,000 engineers and scientists. What they do? They want to land on the moon. Okay, with 10 years of spending, with 10 years of money, and finally, in 1969, he made his promise. In 1969, July the 20th, Apollo program succeeded. He landed on the moon. Neil Armstrong landed on the moon and come back, and that's a big triumphant. With that, United States regained the upper ground in the space race. Okay. Now, I remember vividly in 1969. By then, I was a postdoctor in Seattle. During that landing, there's no car almost on the street. Everybody is glued in front of the TV set. It's real time, not recorded or playback. It's real time. If somebody died, you can see somebody died. If the mission failed, you can see the mission failed and how it failed. Okay, so everybody was looking, watching the landing, and then and Neil Armstrong was running around and eventually comes back. That's all happened in everybody's living room. And it's such excitement that it really grew the whole country together. And then after that, what happened? After that, of course, you go to the second time, you go to the third time. By the third time, nobody is watching TV. People are not interested. So, okay, you launch your satellite, and this satellite actually flew to the moon. In fact, in the next few missions, there are some very precarious situation. The astronaut did not even able to come back because there are some mishap, some accident, but nobody pay attention. So after landing on the moon is finished, Apollo is finished, what to do with this? Well, landing on the moon is a challenge to gain upper ground of the space race, scientifically and scientifically there's nothing following up. You go to the moon, you find the moon. Actually, before you land, we have already understand the moon very well at that time, because before you land the person, you have to know what kind of environment you encounter. They don't know what's on the moon, so you have to study the moon in minute detail before you even dare to go there. So with all that technology, and after landing on the moon, so what to do with this space program? NASA, ever since, has been wondering. NASA has never found a goal, a next big objective. Yeah. Now, I left NASA 2 years ago. The reason that part of the reason I left NASA is after landing on the moon, United States government made NASA a primary research center. So everybody just do research. As long as you do good science, good engineering research, that's fine. They will support you. But then, as the world situation evolves, United States spend a lot of money fighting little war here, little war there, and the government eventually lost the willpower to support good research. And with NASA wondering there cannot find any really big goal, a big objective to concentrate on. So NASA is doing little thing here, little thing there. Occasionally you find the NASA in the news, but this news is nothing compared with landing on the moon. Okay, so about 5 years ago, the President Bush, had a big idea. So he actually called NASA administrator, the administrator then, into his office. So listen, I want to do something big. The administrator was very happy. He said, what do you want to do? He says, I want to go to Mars. Unfortunately, at that time, the NASA administrator is Sean O'Keefe. And Sean O'Keefe is an accountant. He didn't know the science, the engineering side. He immediately said, yes sir, we're going to go to Mars. And he went back. This actually was the second time going to Mars was brought up to NASA. Bush's father, the old Bush, had talked to NASA once. He says, well, we don't have something big to do. Why don't we go to Mars? So he brought the NASA's administrator then into his office. The NASA administrator at that time is Daniel Golden. Daniel Golden was the head of DRW, and he is a member of National Academy of Engineering. He's very good engineer. So when President Bush mentions we're going to the Mars, he immediately asks, says, are you prepared to spend the money? The old Bush says, how much? He says, 400 billion. 400 billion, okay, US. Bush heard that number, and this time Bush was shocked. Bush said, oh, forget about it. Yeah. So he went back, and nothing happened. But when it happened to Sean O'Keefe, it's different. How come Sean O'Keefe can be an administrator of NASA? It's an accountant. That happened again at Daniel Golden. Daniel Golden, when he was administrator, he was looking for something big to do. One of the things that he wanted to do is to build a space lab. So we're going to put somebody in space, and he will do all kinds of wonderful things. For example, grow a big crystal in zero gravity, so that everything will grow symmetric, rather than like on the Earth, you grow unsymmetric crystal. That's wonderful, but that's nothing shocking. Okay, so he proposed a space lab. The space lab does not have enough science to back it up, and the space lab does not generate enough publicity to make the people support it. Space lab, the Russian has space lab first. Yeah. So what's new that you want to prove? Nothing. So, but the space lab costs lots of money. So in Daniel Goldin's watch, when he was administrator, he overspent $5 billion. NASA's total budget is about $18 billion. He spent $5 billion overdraw. Then when young Bush becomes president, he told Danny Goldin, he says, you have to go. We cannot tolerate this deficit spending, even though he deficit spending a lot. He said, well, I cannot tolerate you deficit spending. You have to go. We're going to instead of an engineer, because you don't know how to count money, we're going to find somebody know how to count money. So he brought Sean O'Keefe as an administrator. Sean O'Keefe is not an engineer, he's an accountant. So Sean O'Keefe been told to go to Mars. He said, yes, sir. And he went back to NASA. He said, I've got good news for you. He told his engineering associates, his the NASA, other technical people. So I've got good news to you. We got a big project. People ask him, what's the project? He said, we're going to go to Mars. Oh, everybody is excited to say, fine, that's great. How much money they allocate? He said, well, I forgot to ask. So we have to clarify that. So when he called back to White House says, well, we don't have any money for you. Yeah, you have to use whatever you have to go to Mars. And so when he told the engineering colleague that news, everybody mood definitely changed. So when they look at the book, we have $18 billion. They figure if we spend every cent of NASA's budget into the project for going to Mars, we're still coming up short. And how long it will take? It will take 40 years. Yeah. So at that time, because the president already decided to go, so we have to go. So NASA get reorganized. Now this reorganized is very different from Kennedy's day. Kennedy said, well, I'll give you unlimited resource in terms of money. And here we don't have that money. Kennedy said you can hire anybody you want as long as it's helpful to go to the moon. NASA cannot hire anybody. The reorganization is reshuffle the people. All the people within NASA say, oh, we're going to go to Mars now. We have to do this and that. So NASA was converted from a research institute into a mission-oriented. Our mission is to go to Mars. Yeah. Anyway, that's different. But even go to Mars, that when Kennedy announced that we're going to moon, that's a force to pull everybody together. Now we try to go into Mars by using the available personnel and available resource. It does not really pull everybody together. It actually causes a big problem within NASA. Most of the people say, I don't want to go to Mars. In fact, even before I left NASA, in bulletin board, almost every bulletin board, you can see some comments. Yeah, most of the comments you can summarize is that we can solve all NASA's problem by sending Bush to Mars. Yeah. Anyway, so NASA has been looking for something to do, and one of the things that the NASA at that time want to do is to say, instead of look out in the space, we're going to look back on Earth. Okay. We have satellite, we have radar, we have all the communication capability, and why don't we look back on Earth with whatever radar? But on Earth, you know, if you look back on Earth, everybody have seen, I believe everybody have seen these shots on the moon. You see on the moon horizon, you see the Earth rising. And Earth is a blue planet, because it's all ocean. More than 70% of the Earth's surface is covered by ocean water. If you send any radar back on the Earth, the probability is to hit ocean. And then the problem is that we have to understand what happened to a radar beam sending down to the Earth and bounce back. What does the radar beam contain? If we want to understand that radar beam, then we may be able to do something. Okay, so the ocean surface becomes a concern in the NASA program of studying Earth. Now, this is the historical events happen in the large world. In order to do that, then the instruments proposed to Earth system study are the following. They are altimeter, they are scalerometer, they are synthetic aperture radar, and also radiometry. Yeah, those are the instruments. What is an altimeter? Altimeter is a instrument, a radar instrument, to measure height. Every airplane has one of those. Yeah, and but the airplane altimeter is not as precise, not as accurate. But to do earth science research, you really need a very precise altimeter. How precise? That is, if you launch a satellite 800 kilometers in the space, you have to be able to measure the surface height to be within couple centimeters. Couple of centimeters. It's about that big, less than an inch. If you can do that, it will become useful. And that's a tall order. Okay. Then the scalerometer, later I will explain those instruments. Scalerometer is the same thing as a radar. This radar beam out, but instead of looking vertical to measure height, you look on the side. You don't care the distance. You want to know how much backscatter, the energy you backscatter back. The backscatter power turns out is related to the roughness of the surface, how rough the surface is. And the ocean surface roughness is determined by wind. So if you know the roughness, you can find a relationship between wind. You can measure wind. And knowing the ocean surface wind is very important for oceanographers as well as meteorologists. And they can use that to predict, to make a weather forecast and even make a long-term climate forecast. So the scalerometer is that. The third one is the synthetic aperture radar. And that is an instrument that's very, very powerful. But unfortunately, the United States is not using it to study ocean. The reason, I will tell you the reason. The synthetic aperture radar, most of the radar or camera we have has a real aperture. So you open the aperture, you take a picture. That resolution image is determined by the wavelength of a radar and the aperture opening. If you have a big aperture, you have a good resolution. A small aperture, you don't have a good resolution. Synthetic aperture radar is that we cannot build a radar hundreds of meters or kilometers big, but the radar is moving. I can take a picture here and take a picture here, and then you synthesize the image and getting a picture. By the way of synthesize, your resolution, the radar resolution, can be as good as 25 meters. Yeah, and see, like the radiometry, it's not synthetic aperture, so that resolution is a few kilometers. Yeah, now the synthetic aperture radar is 25 meters. Because the resolution is so good, you look at the ocean, you find all kinds of signal. It's the most amazing instrument that ever built. Unfortunately, it reveals so much, it starts to see submarine. The submarine, you don't see submarine, you see the wake. The submarine, when submarine move underwater. The ocean water is not uniform. Ocean water is stratified. The top surface is the lightest, and the bottom is the heaviest. The ocean water in the deep ocean is 4 degrees C. That's the densest water. So at the ocean surface, the temperature is about 30 some degree in the summertime. So From that, you gradually change to 4 degrees C. The water gets heavier and heavier. When the submarine goes through this stratified environment, it generates internal wave. And this internal wave causes the surface water to flow in a certain pattern. And that pattern causes the wave, surface wave to change. And from synthetic aperture radar, you indeed can see the wake of submarine. The wake 就是船走过去那个痕迹 yeah. And when the U.S. Navy saw this, the U.S. Navy stepped in, says, you don't play with this. This is national defense. Okay, stop. So NASA get an order from the Department of Defense. Says, from now on, you cannot use synthetic aperture radar to look at the ocean. Does NASA use synthetic aperture radar? Yes. What do they look? They look at the Arctic region, look at the ice, look at the land, but never look at the ocean surface. But are they synthetic aperture radars that actually look at the ocean? Yes. Who built it? As long as United States Department of Defense cannot control them. For example, Canada. For example, ESA, European Space Agency. So now, the leaders in the synthetic aperture radar research are in Europe and Canada, not in the United States. Yeah. So we don't have that. And radiometer is just a passive device. You open up the aperture, you receive the reflected energy. Like, for example, using camera. Camera is visual. It's a camera. It's a camera. It's a passive device. You don't send out any signal. You just receive signal. And IR is also, you measure the temperature, and that you can use both optics as well as radar microwave. Yeah. All the instruments need to know the ocean surface. Yeah. So that's where I come in. And this is the big historic event. And this is how I come into the picture. In 1957, I told you, 1957 I was a sophomore. In 1960, I graduated. I graduated from National Taiwan University, majoring in structure theory. I was in civil engineering. Structure theory, what I studied? I studied reinforced concrete. I studied steel structure, timber structure, all kinds of structure, bridge, buildings, and all that. Has absolutely nothing to do with space or whatever. And after I graduated from civil engineering, I decided to go to the United States to continue my study. Yeah. And in that effort, I applied to a university. This university was shocked by Sputnik. They abolished the whole engineering school and reorganized all the different departments into one single department called mechanics. Yeah. The mechanics is very different from the traditional civil engineering, mechanical engineering, or whatever. As an undergraduate, you learn how to calculate satellite orbit, how to calculate the height that you need, the velocity you need in order to launch satellites. They teach that kind of theoretical mechanics course. Yeah. But unfortunately, I wrote to the civil engineering department. I didn't know they reorganized. The catalog I had was an old one. But they accepted me. So I end up in the mechanics department. In the mechanics department, they are fluid mechanics, solid mechanics, all kinds. Yeah. But I went there by all kinds of coincidence. I went there too late. And there's no more slots in the solid mechanics. So I get stuck with fluid mechanics. And once I studied fluid mechanics, I find that my mathematics is so poor. I don't understand what they're talking about, because fluid mechanics, immediately you have to know partial differential equation. I barely know a little bit ordinary differential equation. I don't know anything about partial differential equation. So I have to catch up with that. And in my effort to catch up, I studied lots of math course. So I totally changed from the undergraduate major into fluid mechanics and mathematics. Yeah, and I graduated in 1967. After I graduated in 1967, because my thesis was on ocean surface wave. Who will hire ocean surface wave person? Oceanography, of course. So I went for 2 years of oceanography, postdoctoral training. Yeah. And after the postdoctoral training, in 1969, I started to teach. And that, the two trajectories start to meet. NASA is trying to study Earth. And in order to study Earth, they need to understand the ocean. And I know the ocean surface. So as soon as I start to teach, people come to me. Say, hey, you know something about the wave. We need help. The first job I got, the first question I got is the following. NASA, with all that money, they're still moving at the inertia of the Apollo program, which is landing on the moon. They still get a lot of money. Yeah. So we want to use radar to study the ocean. Yeah. But in the meantime, there's a Navy guy in the Navy Research Laboratory. He took a cheap camera. He took a packed camera of the ocean surface, and of course you see waves. And then use analog Fourier transformation device. He get a wave spectrum. Okay. Then NASA ask themselves, then why we need these millions of dollars to spend on a radar to measure wave if you can do it with a camera? The first question they asked me is look into the problem. So if you can use a camera, then how good are they as compared with radar? So that's my first assignment. So I analyzed the claim that the Navy made. I found all kinds of mistakes they made, and also I found also all kinds of deficiency in using camera. The camera is an optical device. It will be blocked by cloud, and also it's passive device. You need the natural light to illuminate the surface. If the natural light illumination is not optimum, the result you got would be different. Yeah. Different lighting condition will give you different answer. But using radar is different. You have control of the illumination source, so you know exactly what you get back. After this analysis, they like it very much. Yeah. They say, well, we have other problems to ask you. I said, fine. So I start to do research for them. I conducted research in wave research for NASA from 1969 until 1975. Yeah. By the time of 1975, NASA come to me. They offer me a job. They said, why don't you just come over to join NASA? We have big things to do. I said, what's the big thing? The big thing is the sea satellite. NASA said, we are really serious about study ocean. We're going to launch a satellite dedicated for ocean study. On this satellite, there are all kinds of instruments: the altimeter, the scalerometer, the synthetic aperture radar. At that time, Department of Defense still don't know how much the synthetic aperture can see. So they allow NASA to put a synthetic aperture radar on this first satellite. After this satellite, DOD said no more. Okay. So at the time they proposed this, and this satellite is to be launched in 1978. Yeah. And before you launch a satellite, you better know how well the instrument is performing. And so they hired me to make sure that the instrument is performing well. I was hired as the person in charge of the ground truth. So I thought that was a very good job and very challenging job and a lot of money come with that, I can do a lot of good research. So it's fine. So I resigned my teaching job. I joined NASA. But I don't know the politics of doing research. Doing research is one thing. That organizing research is a totally different thing. There are lots of politics. The politics number one is that the CSAT is managed by JPL, Jet Propulsion Laboratory. Jet Propulsion Laboratory is a big organization. It's about 7,000 or 8,000 people, managed by Caltech. It's a very powerful organization. But when they got the CSAT satellite, they cannot give the ground truth mission to a different group. They don't want that. See, logically, you should have, you launch a satellite, I will tell you whether this is truth or not truth. But the JPL think that's too risky. So suppose I launch a satellite and some other group comes in and says, well, this is all the satellite data is no good. So their lifeline, their success or failure will be dictated by whoever the judge is. So they say, that's no good. We want to be the player and also the judge. So they don't want to give this truth team to other center. So I joined a very tiny center. And that tiny center's main claim of fame is altimeter. So JPL fought with NASA headquarters and took back the ground truth team. So we want to manage that ourselves. So that bad. So without that, I don't have a challenging job. But fortunately for me, when I joined NASA, I have one condition. I said, listen, if you want me to go to join NASA, one condition I have, I will do whatever you want me to do, but you have to build me a laboratory. NASA said, well, what kind of laboratory you want? I said, I want a big wind wave tunnel. NASA sent an engineer down to my to the school that I was teaching and look at the little tank. I heard, this is the tank? That's easy. I said, no. The tank I want is 10 times bigger than this. NASA said, no problem. You come over, we'll build a tank for you. Yeah. So they promised to build me a tank. And that tank actually saved me, because without the big job of managing as part of the satellite program, I was able to concentrate in the laboratory to do a lot of study. So I joined NASA and joined the CSAT. And the first thing I did was a lot of work on altimeter. Why altimeter is important and why altimeter can give us is related to the wave. The altimeter is a satellite that you measure the height to the ocean surface. And this, in order to measure the surface, as I say, to be within a couple of centimeters, you need to know a lot of things. First, you have to know your position. So if you don't know your position, the distance you measure is relative. Yeah, you can always measure the distance with a precise precision, but you cannot measure a distance with accuracy. Accuracy means absolute. Precision is relative. Yeah, like you have a very good gun. You can shoot the target. You always have a very tiny cluster, but it's way off the target. Yeah, so you want to be on the target and have a very tight cluster. So to do that, you need a satellite. Can we turn out these lights? I don't need the light here. If you turn out lights, this view graph will be better. 可不可以把这个灯关掉？我开了，他们也看不清楚。所以我们就好像现在也是黑黑的一团的，会比这个还坏吗？不，他们假如这样的话，他们更看不见这个。是我的脸比这个不重要，对不对？那电门在哪里？我来关，我们来试一试啊。 没关系。这个这样你看比那个好得多吗？啊，还可以啊，还可以啊。他们讲你，我们也听不见嘛。你说，你们喜欢这个荧幕亮一点，还是喜欢我脸亮一点 ？Hello， 好。
台大跟听的同学，这个画面喜欢吗？台大。
荧幕亮一点可能好一点。
这样子，那静怡呢？静怡，没有吗？那就叫台大意思吧。
So you measure the distance from the satellite to ocean surface. Then you have to track the satellite very precisely. And typically you use laser to track the satellite. So you know precisely the orbit to be very, very accurate. And after you measure that, then of course you can measure the ocean surface. The ocean surface will be very precisely measured, and also precisely measure the length. So that's essentially altimeter. The main mission, the main function of altimeter is to measure that distance. But there are other other ancillary data that can be used for other purpose. Once we measure this, what can we use the altimeter? We can use to help navigation. Yeah, it measures the distance, and from that distance, actually you can back out other things. So predict the sea floor depths even, and that will help plate tectonic and give us geoid primarily, and also give us sea surface level change, and imply that will have the global warming implication, and measure ocean circulation, and also wave and sea state. Yeah, I will explain this little by little why a single satellite can do so many different things. And first, geoid. And if you can measure the distance to be a few centimeters, you measure the ocean surface. The ocean surface, when we ask you, so what's the ocean surface? People immediately say ocean surface is a flat surface. Ocean surface, even after you average out the wave, ocean surface is not flat. Ocean surface undulate up and down according to the geoid. What is a geoid? Geoid is equal potential surface. The force over there are all perpendicular to it. It's equal potential surface. So the force is perpendicular, and if we measure the geoid, which is the equal potential surface of the Earth is not a perfect sphere. It's not a pear-shaped either. It has a lot of up and down, high and low. This up and down, high, low can be tens of meters difference globally. Yeah. Typically, the ocean, the geoid is lower. Why the ocean is lower? Because the ocean bottom geological structure, the crust density is much heavier than the land. So land actually are something float on the underlying layer, which is near fluid. So the whole land is not a flat, and the whole ocean is not also not flat. Yeah, and not only this overall high and low that you can see, locally the geoid is so drastically different. Like for example, here is a small section of a geoid. If you measure that geoid, that ocean surface actually goes up and down, almost like a smoothed copy of bottom topography. Yeah, the geoid, the very dramatic thing that you can see the geoid is that if you go near a seamount, a mountain in the ocean, the fact that a seamount can exist, that means locally the seamount density is lower than the other part of the ocean, which is primarily basalt. But once you have a lighter material there, the gravitational attraction will be lower. So the ocean surface near a isolated seamount will have a dome coming up and coming down. This coming up and down in the typical seamount is about 5 to 10 meters. Yeah. So if you measure the ocean surface, you'll find a local dome there. It's about 5 meters. And if you go to a sea trench, like a Mariana Sea Trench, 16,000 meters. And if you go to a sea trench, the fact that you can have a trench means the local gravitational force is very strong and actually pull down that. So the sea surface near the trench can deep down 20-some meters. Yeah. So this up and down, if you measure, it's so detailed. Each little bump, it reflects on the sea surface. Then you may ask, so well, in that case, if I encounter a seamount, I will steam up, a ship will steam up and steam down. So in the up end, I probably have to spend more energy because I'm going up and then coming down like a hill. Turns out it's not that, because the whole surface is equal potential. Moving on equal potential, you do no work. And if you put a marble on this bump, this marble, 一个球, will not roll because the force is perpendicular to the equal potential surface. Yeah. Now, why is this so important? This is so important is because this geoid, the ocean surface, typically reflect a geoid. Yeah. This geoid is very important. It has military implication, military applications. As I said, if you have a seamount, your local surface can come up with, say, a few 5 meter to 10 meter. You have a trench, you can deep 20-some meter. So the local force are all like this. See, this is a mountain. The local vertical is like this. It's not all vertical are all point to the center of the earth. The local if you have a plumb line as a weight, you have a plumb line. That plumb line will go like this. This plumb line go this plumb line go that. So the plumb line of local vertical is not exactly geometric vertical from the center of the earth. So it has some inclination. You come to the seamount, along the seamount, because all the forces are perpendicular. So if you use a plumb line, the plumb line will keep changing. And that angle turns out to become critical to submarine. The submarine, everybody knows that during the Cold War, the United States and Russia both has very, very powerful submarine. And the submarine can hide in the ocean for months in end. It can cruise to any place, and it can launch satellites, rockets to attack each other. Now, to launch this missile, you want to know which angle you send the missile out. And that angle, the reference of that angle is local vertical. So from vertical, I launch, say, 30 degree, for example, okay, 45 degree, whatever degree that you choose. But if your vertical keep changing like this, then exactly which degree you want to launch your satellite. And this satellite, or not satellite, the missile, the initial angle can be off tiny. But then remember that missile will go thousands of kilometers. So a tiny change of this will change the target tremendously. And as a result, this geoid is classified. Yeah. Oceanographers don't get the geoid. The altimeter data come down back to NASA. NASA first take out the geoid. They don't tell you what kind of geoid. To give you a rough reference surface, a geoid which is not of use to military. Yeah, to give you that reference. And the real geoid, the detailed geoid, is classified. Yeah. So that is very, very important. And so you measure the ocean surface deep down, and then it will come up. This is the geoid shape. This is the geoid shape. So near the seamount, it comes up. Near a deep ocean, it deep down. The geoid keep wandering all over the ocean. Now, as I said, if you can measure the sea surface, then you can monitor, say how far the sea surface come up and how far the sea surface going down. Everybody is now talking about the global warming. Says, sea surface is rising. And one of the scary story that the global warming, the consequence of global warming is that the sea surface is going to rise up. And you see this sea surface, if it rise up 1 meter, it will flood a certain area of the Earth's surface. So if we have an instrument that can measure global surface, then we certainly should be able to tell how fast the sea surface change. Now let me show you some data of how sea surface change. The sea surface change from from now to 24,000. That means 24,000. That's 2,000 年, 24,000 年 ago. The sea surface now, say we use sea surface now as 0. We always use sea surface 0 as a reference. If you have a 0 reference and we trace back to 24,000 years ago, where's the sea surface? The data indicate the sea surface is lower, more than 100 meters. 100 meters lower than now. Yeah. Why is that? Because 20-some thousand years ago, we have a big ice age. A lot of water is locked up on land in form of ice. The ice, there's so much ice, yeah, that the glacier came down from the North Pole all the way to present-day New York. Yeah. In Europe, it covered the whole England island, yeah, all the way to France. Yeah. So everywhere is ice. This big chunk of ice lock up the water, and as a result, the sea surface is about 130 meters lower than now. And as we come out of the ice age, more ice melt. The sea surface starts to rise, and rise until now. It's here. So the sea surface has been rising over the last 20,000 years. Yeah, the last 10,000 years were pretty stable at the present, near the present level. Yeah, at this time, the sea surface is 100 meters down. We'll come back to discuss this. The sea surface is so low that the Bering Sea, the Bering Strait, separate the Eurasia landmass and American landmass, is already exposed. So the people can walk through Bering Sea, and indeed people did that. And who did that? The American Indians. There's absolute no humans, Homo sapien, like people in the American continent until 20,000 years ago. All the people come out of Africa, eventually they migrate and end up there. That's the consequence of this, sea level low. But that sea level change, this 20,000 years, of course, is too far back. And if we look at about near 100 years, the sea level, even though we look at very flat, the sea level is still climbing. 35, 30, 20, 10. But you have to notice, the unit instead of meters now becomes centimeters. The order of magnitude is 100 times lower than the previous view graph. Yeah. So the last 100 years, the sea surface is still increasing gradually. Is that due to the global warming? Maybe. Now, the last little tiny piece is in red. And the red part is this. And this is the data analyzed by Dr. Chen, sitting in the back. Yeah. And this sea level change is actually measured by satellite altimeter. Satellite altimeter goes through the Earth, measure the height, and you average the whole globe, and you plot out the sea surface change. It looks like this. And you can see that each up and down, up and down, up and down, there actually is annual cycle. Each year, the sea surface fluctuates. Yeah, within a year. And this increase, the unit, the unit here is again centimeter, from -20 to +20 over the last about 16, 15 years. So that is the kind of sea surface change. Yeah. Now if you read the newspaper will tell you the rate of sea surface change is this black line, the trend. Without proper data analysis, the only thing you can get is to draw a straight line. So that's the rate of sea surface change. Yeah. And that sea surface change is 3.2 ±0.4 millimeter per year. And that kind of sea surface change is the newspaper article or whatever you read. Not only newspaper article, even the IGPP, Intergovernment Climate Change Panel, still use this kind of number. Why they use this number? One is that this is the only way that they know how to determine it. Second is that this simple number is so simple that you can actually present it to the policymaker. The NASA administrator once told me, says, don't give me too complicated an answer. When I go to the Congress, I have to tell the story, the result to them. That the average math background of the congressman, U.S. congressman, is 4th grade. They barely know plus minus, okay? Don't even give them division or multiplication. And if we go through this course, HHT, you will be able to do like what Dr. Chen did. Instead of draw this black line, you will draw this red line as a trend. The red line and black line doesn't look that much difference. It looks very similar. But what is the dramatic difference is that if you take a derivative of this black line, you get this sort of pink line. It's constant. 3.2 ±4. Yeah. 3.2 ±0.4. Yeah. But if you use this red line, then you take a derivative, you find it curves like that. So the sea level rising is not constant. Okay, it's rising pretty fast here, but you can almost see it start to bend back. Yeah, and I think this is important. Scientifically, it is important because you have to find out why we have this fluctuation. World, you will hear this repeatedly from me. World is not linear. You cannot draw straight lines going through the data. So this is the story about sea level. And in the course, we'll revisit this later in the course after we learn all the technique. I will use this data as an example to discuss how we analyze this data to get this kind of thing. And ocean circulation. If you measure the ocean surface to be so accurate, then you will find that the ocean surface is not flat, not only because of geoid. Geoid is big signal, tens of meters. Yeah. But other than that, they are ocean dynamics, dynamic signal. What's ocean dynamic signal? That is when the water is moving, the ocean surface is not flat. Not because of wave. It is because of other things. I don't know whether you watch Weather Channel to see the weather forecast day after day. Anybody watch this Weather Channel? No. Oh, well, you doesn't count because you work for what? Okay. Yes. 啊？你们上什么课？啊？微积分啊？我们不上微积分的，你们走错教室了。Anyway, so the ocean surface, when the water is moving, is under geostrophic balance. The geostrophic means pressure balance. So if you watch the Weather Channel, you will see we have high pressure, we have low pressure. You should pay attention to this because that the Pacific high actually actually made us so miserable that the last typhoon doesn't move because it's get in between two high pressures. Has no place to go. Yeah. So typically you have high pressure, you have low pressure in the weather system. But if you look at the wind, if you have water from high to low, you flow from high to low. If it's a direct line, you can flow direct line from high to low. But when the scale becomes so big, like in the geophysical scale, the water does not flow from high to low anymore because the Coriolis force, the Earth's rotation, comes into play. When you fly down in the northern hemisphere, the Coriolis force will make the water turn right. Yeah. So the wind field actually is flowing around a high or around a low in a dictated by the Coriolis force. And that balance, Coriolis force, exactly balance the pressure built up by the high and low. So we have Kuroshio, we have Gulf Stream. Across Kuroshio and the Gulf Stream, the ocean surface on the open ocean side and the coastal side, ocean surface actually can have 1 meter height difference. In other words, you go to the open ocean is high. Yeah, you come to the coastal ocean, the sea level is low. And across here, you have 1 meter high. So the water try to go from high to low, and the Coriolis force, you have to turn right, so the water go that way. So Kuroshio and the Gulf Stream are the same thing. They are about 1 meter high. Not only that, you may even have these eddies. When the eddies flow, the inside eddy and outside eddy may also have half meter height difference. If we have height difference, then we can we can measure that. And this is a 5 years average. Then we can start to see this is the Kuroshio system and this is the Gulf Stream system. We can actually, using the height difference, we can calculate the velocity of the ocean. Not only that, we can have equatorial current, we can have circumpolar current. All the major current systems showed up from altimeter. And if you use TOPAX 4-year average, you can see that there are lots of energy here. This is Japan, and this is the this is the Kuroshio, and this is the Gulf Stream. Yeah, using satellite, you can do that. And why satellite? How satellite measure these things? Satellite send a pulse. A pulse will coming down. This pulse is very, very narrow. Yeah, the pulse is about a few meters wide. So when the pulse first come down, you don't have any signal. You don't receive any signal. This is time. You don't receive any signal. As the pulse first touch this, you start to send signal back. You start to have signal coming back. As the pulse coming even further down, you get more illuminate, larger area. So you have a larger area. But this area is limited because only this part has radar energy. So after that, it becomes something come back. So you get a donut shape. So the amount of power coming back is saturated here and start coming down. So each time you measure the ocean surface, the radar actually come back like this shape. Yeah. But this is for a perfect flat surface. Ocean is not perfect flat, not only because geoid, not only because of ocean dynamics, but because of ocean waves. Now if I turn on the waves, that will be totally different. Because you have wave, you're coming down, first you touch the crest of the wave. Once you touch crest of wave, you start to bounce back. But this bounce back is nothing regular, because the wave is irregular. And then you go even more, and it will bounce back even more, and bounce back even more. So it start bounce the back scatter again, roughly look like that, but it's not exact like that. It's not exact flat. And this curve compared to the flat surface is also different. And not only that, when you have a satellite, you send the radar beam down the ocean surface. If you send the radar beam down to a flat surface, it bounces back vertically. Your satellite sits right over your head, you get your signal back. If you send the satellite to this surface, which has a slope, then the local vertical like that, so the radar beam bounces away, and you send here, it bounces away like that. So the only signal you got back is actually the part that has a flat surface. Yeah. So using altimeter, do you really measure everywhere of the ocean surface? Perhaps not, according to the theory. Yeah. So you have to know not only the probability distribution of surface, you have to know the slope just right to get it. So in order to explain the ocean, the height you measure to be within 2 centimeters. So if you measure within 2 meters, you can forget about this, because the wave height is the average couple meters. Yeah. But if you talk about a few centimeters, then whether the signal come back from the crest of the wave or the trough of the wave make a tremendous amount of difference. Yeah. So because of that, this return the signal is not this flat line anymore. This return the signal, sometimes it go like this, sometimes it go like that. What determines that? The wave. And in fact, this radar is performing a Lebesgue integral of the ocean surface. What's the Lebesgue integral? You first get the highest, then get the second highest layer, then get the third highest layer. Eventually you come down. So that is a perfect cumulative surface height probability density, probability distribution function. Yeah, not density. You take a derivative of this, it's almost near Gaussian. Yeah. And then how to determine this surface, this slope, how to interpret the slope. And the way that we actually measure the ocean surface height is to take the midpoint of this slope. The midpoint of the slope, then because of this midpoint of slope can be either here or there, and that gives you a difference. That difference is more than a couple of centimeters. And that's why when you come down to a couple of centimeter determination of the ocean surface, you have to, surface mean level, you have to know the probability. So when I first get there, they'll talk about this measure altimeter height, this with the profile. And the approach is that the surface are important to determine the surface height if the precision is within a few centimeters. Yeah. And the traditional assumption is that because there are so many ocean waves, and one wave is independent of the other, therefore by central limit theory, the wave surface height distribution has to be Gaussian. Yeah. So they use a Gaussian distribution. If we use Gaussian distribution, then the problem solved. But is the wave Gaussian? The ocean waves are nonlinear, which produce asymmetry, up and down asymmetry. And altimeter get a return, not from the ocean surface, but from the specular return. It's like a little mirror. That mirror have to be pointing to the altimeter. So we need a elevation slope joint distribution. And not only that, that joint distribution determines the height that you measure. So if, for example, if I say that I see an ocean surface, the ocean surface look like this. Will anybody agree with me? So that look like an ocean surface? No? Why not? Why you think this is not an ocean surface? It doesn't look like an ocean surface, right? Given that the ocean surface is covered with waves. Why it doesn't look like an ocean surface? Because we know the ocean surface look more like that. So why look like that? Because the crest is always sharper. We have never seen a very sharp trough. See, the trough of the waves is never sharp. The crest is sharp. And that is because of the nonlinearity of the ocean surface wave. Now, if the ocean surface look like that, if this is the mean water level, then we add up the probability distribution function. We get a lot of this flat surface over here. And then we get a few of the extremely high wave over there. So the distribution is definitely non-Gaussian. Gaussian is symmetric. So the water surface has the up and down asymmetry, surface height. And this was not known because people study ocean wave always assume it's Gaussian distribution. And the first people actually measure the ocean wave was in the 40s. And when I met Professor Lonke-Higgins from England, he was the Royal Society chair professor at Cambridge University. He said the first distribution that he ever made, they spent a couple months. They found a graduate student, set the graduate student at the desk, digitize the strip chart recorder of the ocean surface wave, point by point, point by point. Took 2 months to digitize enough data to plot a distribution function. And because the wave is, the measurement, the sea condition was very mild, and he get almost near Gaussian. So people say, see, it's almost near Gaussian. Well, but if you look at the ocean surface, you know the ocean surface is asymmetric because when I draw an ocean surface profile, the profile looks different. Okay, and if you look at the Moore wave, the high sea state, especially under a very, very large wind, high wind, the sea surface look really random. And that make Lord really say the basic law of the sea wave is the apparent lack of any law. He says, I cannot really describe the ocean surface. And that was, of course, corrected by the sea surface probability model. And sea surface probability model, we can say that if I have zeta 1 equal to A cosine chi, if A is really chi is uniform, zeta 1 will be normal. Okay? And same way, if zeta 2 is A sine chi, chi uniform A really, and that's normal too. So you put all two together, you will have the joint probability is also normal distributed. So sea surface based on this is normal distributed. But then we know from nonlinear analysis, we find that the zeta actually is not just simply A cosine chi, but A cosine 2 chi, 3 chi. This is by perturbation analysis. And this is known for 150 years. The first person did this was Stokes. Stokes in 1847 derived this expression. And as a result, people still call this wave Stokes wave. And if you take this derivative, take this derivative becomes ak sine chi, ak squared sine 2 chi, and so on and so forth. Then if you define zeta minus zeta bar mean divided by the standard deviation as eta, and define cx slope minus slope bar divided by its standard deviation as c, then we have two nonlinear variables, eta and c. And each of this is related to the surface height. Then there is a fundamental theory, and then you can, if we define capital Z as this, capital Z2 as the sine part, and we can write this as Z1, Z2, and you can actually solve eta and Z as in terms of zeta 1, zeta 2. But we know the distribution of zeta 1, zeta 2, Z1, Z2. Then can we write the distribution of eta 1, eta and Z? Yes. That's by a fundamental theory of the water probability theory. So you solve zeta 1, Z2 as eta and C. You can actually solve this equation, solve for Z1, Z2. And once you solve Z1, Z2, you find a critical important parameter is called the significance slope. And that significance slope will give you, we'll come back to that. And once you know Z1, Z2, the probability is Gaussian, then the probability of zeta 1, zeta 2 is Z1 in terms of C and zeta, Z2 is C zeta, times the Jacobian of that. This is Jacobian of the variable. This is the fundamental theory of probability. Okay. And once you do that, and you find that the joint distribution of eta and C, the height and the slope, is given by this Massey equation. This equation looks messy, but it's straightforward. It's, if you know high school algebra, you should be able to solve this. Yeah. And once you solve that, if you look for the height distribution, the height distribution, if the slope is near zero, a very tiny wave, the distribution is indeed Gaussian. And as the steepness increases, it increasingly becomes non-Gaussian. It becomes this. And this, at early 70, this wasn't known. Yeah, people don't know how it becomes non-Gaussian. Yeah, how it deviates from Gaussian. So the first thing I did was to verify this. This is the tank I asked NASA to build for me. The total length it's about 100 feet. Yeah, 100 feet. It's 27 meters. Yeah, it's much longer than this. Much longer than this. The height is 5 meters. It's taller than this this room. It has a water channel part and has a big fan to send the wind down, and has a big pump to send the water current. So I have a wind wave current interaction. So I will be able to study this. And in this tank, the first thing is to measure water wave height. Yeah, I measure the wave height and calculate the distribution. Yeah, this actually is the first among one of the first thing that I produced. This is a distribution, and here inside here is a dotted line. The dotted line is totally buried by the data. It's very near Gaussian. This is a very mild wave, and if I blow the wind stronger, the wave becomes non-Gaussian. This is the Gaussian distribution. So in that little tank, I was able to prove that the ocean surface indeed gradually changed from Gaussian to non-Gaussian. And I remember vividly when we first generated this, the excitement that we have. And to get this curve in my tank, it takes a couple hours. Yeah. Because there are more than one curve, there are many, many curves we add together. It's repeatable. Yeah. And when one of the curve we plot, like I think it's very near this one, we plot in front of Professor Lange-Higgins, and he cannot believe his eye. That's when he told me the first probability density function that he ever produced took almost 2 months to produce. Here, we produced this curve in a couple of hours. And that was done in the late 70s. At that time, I have already joined NASA, and NASA gave me a lot of money. At that time, money is still not a problem yet. So I was able to buy the first programmable calculator. Yeah. Built by Hewlett-Packard, about that big. It has a 27K memory. 27K memory. That's unknown at that time. So when Lange-Higgins come from England, look at my little calculator, which has 27K memory, he immediately took out the notebook, copied down the manufacturer, the specification, all that, and tried to buy. That 27K memory is probably less than a handheld calculator now. I think most handheld calculator has more memory than that. Anyway, but that was the first data we produced, and that ended up be published by Journal of Fluid Mechanics. Yeah. And then how about the joint distribution? Joint distribution, we have to prove it. To prove joint distribution, we need both height and the slope, because only height is not important. NASA doesn't need a height. NASA need a height and a slope, because the altimeter actually look down the specular return. So I built a probe, a wire probe, which measure 4 height at the 4 different locations. And from the 4 different locations, I can compute slope from X direction, slope in Y direction, and the height. And I have redundancy to compute this. And so once I got the height and slope, I plot the height in this direction, slope in this direction. I get a joint density function. And that Massey equation gives me a joint density distribution for that slope come out to be almost near a concentric circle. And it's a little bit of slight deviation. And the measurement looks sort of similar. And if I increase the steepness, it becomes increasingly skewed, and then this side is also increasingly skewed. And if I did more, and the theory predict that, and actually measurement predict this. Yeah, and this was very exciting at that time, because we not only measure just the elevation, but we actually measure the elevation and height distribution. And what altimeter will see is not this whole thing, because this is the height, this is the slope. Altimeter only look at the zero slope, only look at that line. So if I take a cut of this line and compare the theory with experiment, that's the conditional distribution of joint elevation and zero slope, that looks like this. For very gentle wave, it's almost Gaussian, but has a slight slant. You can see a slight skewness. But for higher slope, and this comparison looks like this. And if for even more, the comparison look like that. And this we were able to demonstrate that the nonlinearity of the ocean surface wave really is important. Yeah, and if you try to get the mean curve under there, the zero moments, And this zero moments is very different from the Gaussian zero moments. Yeah. So that's why the wave is important in radar altimeter application. And from that, one can actually deduce the C-state bias like this. You can measure the actual height and versus the height determined by the joint distribution. And that's different from zero. 10% of the wave height, 20% of wave height, 30% of wave height. This is actually the data. And this actually comes from the theory. The theory and the data does not perfectly agree, but they agree within with a qualitative agreement, and the agreement is really much better than anything people can come up at that time. And the conclusion is that based on this simple nonlinear wave model, we can establish a non-Gaussian joint elevation slope distribution. But this model is only approximation, because I used a dominant wave. But the dominant wave has only the big wave. The small wave, when the wind blows over the ocean surface, the ocean surface has lots of little wavelet. The little wavelet is riding on the big wave, and I didn't consider that. But this little wave, what actually saved me, what actually made the experiment agree with the theory, is that this little wave is pretty uniformly distributed on the surface. So when you look down, you actually see the big waves, not the little wave, because the little wave is nearly everywhere. But is it exactly everywhere? Probably not. So it's really a good approximation, a very good approximation. Now, the uniform coverage of the wave with a large wave approximate will work well. Yeah. So I built a theoretical model. The theoretical model is based on large wave only, but because of the small wave uniformly cover the large wave, so I don't care whether the large wave, where the small wave is, I just assume it's uniformly distributed. But is it exactly uniformly distributed? Probably not. And that's why there is a slight discrepancy. But qualitatively or semi-quantitatively, the model works well. Yeah. Now, so indeed, comparison with laboratory wave observation show that there's a good agreement which support the hypothesis of uniform distribution. If it's without uniform distribution, we should have a very different answer. Yeah. Now, the comparison that I have here is only with laboratory wave, but I think it probably works with the ocean wave as well. The result could be used to determine the C-state bias of the altimeter. I produced this result. It was regarded very nicely in the research community. But when NASA used it, no. NASA said, we don't care. This is a little laboratory thing, and you have all the theory supported. We want to do it empirically. So instead of actually use the theoretical result, they flew a very expensive mission using and carry a radar altimeter and measure all the sea state, and then try to average and the different wind condition and average eventually deduce a empirical sea state correction. Yeah, that's how they did it, and this is how I did it. So with this, I will conclude the first talk introduction. And the moral I learned from this is that if we consider nonlinearity, it actually helps us. So nonlinear is important. Nonlinear is not irrelevant. Okay. What I did here is a probability. The probability distribution has an underlying assumption. The underlying assumption is that stationarity. The process has to be stationary. If I try to build a probability distribution, if my wind field is not uniform, I blow the wind strong and blow the wind light, can I make an average, make a probability distribution out of that? No. I have to keep the wind constant to produce one sea state wave condition. I blow wind stronger, I produce another one. You see, the different wind produce different probability distribution. If I have a mixture of wind condition, I will never get a probability. And that is the problem. So you go out in the ocean, will you have uniform wind field all over the world? No. You may have wind uniform over a small area. The case in point is that if you look under the hurricane, you will see under the perimeter of the the typhoon, you have one sea state. You go away, you have another sea state. So the open ocean is a very inhomogeneous wave field. So when you build probability density function, you have to remember that the stationarity is a condition. Stationarity is a mathematical term. If you translate the English, it's homogeneity. The population has to be homogeneous. Yeah. We want to find out the average height of the class. That's everybody in the class. They are all students. We cannot mix this population with something totally alien. Yeah. So that is a big condition. Yeah. We will, in this course, we will challenge the stationarity. This particular example illustrates nonlinear is important. Yeah. I'm going to keep stressing this point. Nonlinear is important, non-stationary is also important. Yeah. And that's why we want to do HHT. Yeah. So this is a little bit triumphant of knowing nonlinearity, the importance of nonlinearity in determining probability. Yeah. Even though NASA did not exactly use this as the tool to determine sea state bias, the sea state probability structure is determined from theoretical side and also verified by laboratory experiment. Yeah. I think after this, not many people want to do probability because it's done. Yeah. So I was told that this class is 2 hours, that I give you hour and a half lecture and leave half hour for discussion. So the floor is open for discussion. Any questions? Question? No? Let me make a make a pool. I use broken English. Anybody understand me perfect? 你们是不是全都懂我讲的话？啊？全懂的举手，全懂的不举手。大家都懂，全都。我发现这个铺没有意义的啊！我说全懂的举手，没有人举手；全都不懂的举手，也没有人举手啊！你们听得怎么样？Give me a guide. What's the percentage? 一半，80%，一半也点头，80%也点头，到底是一半还是80% ？It's different. Do you understand? You should. Yeah. Okay, so we're the same. 你们怎么样？所以how about I mix English with Chinese will not help the Japanese 考了一个。你们这里面有人懂日文的？没有人懂日文的，我要一个 local 翻译。没有啊 ，OK，台大的，我这边讲他们听讲啊， 台大的你们那边听不听得懂，还是听不听得见 ？To begin with， 我讲话你们那边听得清楚不清楚？
还算清楚。
清楚。你们听不听得懂？
听得还蛮清楚的。
还蛮清楚啊。
我们是有一些问题的。
有问题。好，那你们来先问问题。我们现在这个 floor open。
各位有没有什么问题想问？如果大家没问题，我先来问一个。
好。
就是说，你做的这个研究呢，就是说你去 measure 那个，就是说 sea level， 那是不是就是说你相信，大体上在一个 local 区域，它的那个形状，如果说我们 disregard 它的那个 disturbance， 是不是你相信它大致上会有一个固定的形状？
你说 probability density function 啊，还是 sea surface？sea
surface。就是说你，因为我们去 measure 那个东西，那是不是表示说 locally， 就是说一个区域，它里面的那个形状，我们如果 disregard 它随着时间的那个 disturbance 的话，就是说它大致会有个固定的形状在那边。对，
它大致的形状是这样啊，它大致的形状是 described by 那个 nonlinear model， 但是你要知道这个 nonlinear model， 假如我 go back 啊，等一等啊。假如我 go back to this equation 啊，这个 sea surface 啊是 described by perturbation， 这个是 first terms a cosine theta， 假设这个 wave 是 cosine theta， 但是呢，我们知道 nonlinear 那个我们的 differential equation 是 nonlinear， 所以我用 perturbation 呢，我又得到第二个项，又得到第三个项啊，这几个项里面的在 deterministic 叫 Stokes wave， 假如我们真的到了 ocean 里面。这个 A 跟 Chi 都是随机的，都是 random. They are all random number. So when you say that whether if I look at the local area, 这个 ocean surface, whether the ocean surface is or is not a fixed form, the answer is no. There's not a fixed form, but it has the statistical probability distribution function which is fixed. Because this A and Chi are all random. You will never see any two pieces of the surface look exactly the same. But if you accumulate many waves, you will get a density function. The density function is described by what I show as a final result.
Okay. So I have a problem regarding the variables A and the Chi. It seems to me that A is some sort of amplitude of this wave.
Yes.
And what is Chi?
Chi is the face of the wave.
The face.
Yeah.
Face of the wave.
Face is actually the typical expression of this Chi is K dot X minus sigma T plus small phi. That small phi is a random phase. The wave, given a wave, it propagates at a given phase velocity. But in addition to the phase velocity, there is a random shift of phase. Yeah, that's the probability model of the ocean surface.
Thank you.
If you don't have this random phase mix, you will have a deterministic wave. If you have this random phase mix, you will have a random wave. Sometimes come a crest, sometimes come a trough. Yeah.
Okay, thank you.
Okay. Yeah. Any questions? Comments? 你们
喂
Yeah. Oh, I have another question.
Yes, we do have a question.
Sure. Go ahead.
Yeah. Would you please just give us some brief introduction to stationarity?
Okay.
Insight, or just some very,
non-stationarity.
just give us some feeling what the stationary is.
Okay. I will go into that when we discuss HHT, but I can give you a short answer here. Stationary and non-stationary. Stationarity has a very precise definition mathematically. So if I have a cluster, a set of variables measured in a given field, like zeta t at a given time, okay, I measure zeta t, zeta 1, zeta 2, zeta n. I have a set of n variable measured at a given field at the time t. Stationarity means that if I take t plus tau a later time, I also measure all this zeta variable, and this zeta 1, the variable at the t and variable at the t plus tau are identical. That means stationary. Now, of course, for a random field, you cannot have in everything in detail to be exact. So what you will have is you want to demand the statistical property are exact. Then that means the statistically stationary. For example, if I measure n point at the t, I measure n point at t plus tau, then if the average stay the same, standard deviation stay the same, moments, all the statistical moments stay the same, then I say this is stationary. So stationarity means all the probability measures are identical. Okay, and that's stationary. Non-stationary has no definition. So if it's not stationary, it's non-stationary. So the stationarity definition is not quantitative, it's qualitative. The answer is yes and no. It does not have a degree. So suppose I measure 100 points, and I measure later another 100 points at the t plus tau. 99 points the same, 1 point is different. Is that stationary? By mathematical definition, it's not. But to everybody, it's, oh, that's near enough. Yeah. So we do not have a degree. Now in HHT, we'll introduce a degree of stationarity later, once we introduce HHT analysis. Okay? We'll make that definition, instead of qualitative, we want to make it quantitative. Is that clear?
That's great. Thank you.
Okay. Yes. Well, linear nonlinear is come from the linear algebra. This again is just like a stationary, non-stationary. Linear has a very, very strict definition: proportionality and superposition. Yeah. If you have a variable a, and you put in a function, and the function give you, say, f of a. Yeah. And if you have a to a, then the answer is proportionally increased. So anything like that, and also you can superimpose two answers. Anything like that is f a plus b equal to f a plus f b. Yeah, that's linear. We'll come to that. Give you the mathematical definition too. That's linear algebra. However, many system, to be able to do that, you need input and output. But many systems we don't have input and output. So from the system point of view, the most